Hello again, Physics 2 people. This is our first video on inductance, and it's actually, even though the idea of inductance is not, or of an inductor, is we haven't quite gone over yet. You've already seen all the math and technology you need to calculate inductance. So I'm just mostly pulling together a whole bunch of little things that we've already seen to produce a result. For those of you who had linear electrical circuits, you should be familiar with this concept. There are inductors, and you sometimes talk about what's called self-inductance and mutual-inductance. And just a warning for those of you who took linear electrical circuits, in that class you learned about a convention for minus signs with dots, and I can never remember what the conventions are. So I will be able to kind of bring you right up to that edge, but I won't be able to quite connect things up because I can't remember how the conventions work in that case. But you'll see the idea. It's just a minus sign issue. All right. So an inductor is going to be some sort of a current. I don't know, call it I1. And what we're going to look at is the EMF that it either creates on itself. So, and where this is a time-dependent current. So this is a time-dependent current. And so by having a time-dependent current, it creates a time-dependent magnetic field, which will, in this case, induce a flux through itself. Okay, so it's like a self-flux of magnetic field, which means that there is an EMF generated along this coil. So an inductor is a device which uses these time-dependent magnetic fields to generate EMFs. And you can have a self-inductance where the coil induces an EMF in itself, or you can have mutual inductance where maybe there are two coils and one magnetic field will feed through the other, and so the time dependence in one current can create an EMF in the other current. So that's the basic idea of an inductor, and how you can use inductance in a circuit. Before we derive any equations, I want to start with a basic observation. So an observation that magnetic flux is caused by a current. Okay, so that's just an observation. So what we want to do, and let's have a picture in our mind just so we're really concrete here. So I have a solenoid with current flowing, and we're going to imagine that the current is time dependent. So we know Faraday's law says that the EMF results there with my E. So the EMF would be between the two ends of the solenoid. The EMF equals minus the rate of change of the magnetic flux. But if you think about it, well, we can write this we can use the chain rule. So we can write this as minus d phi di times di dt. So we're going to have a time-dependent current, which creates a time-dependent flux through itself. And writing it this way kind of captures that. So this gives rise to the time-dependent EMF, or this would allow us to understand the time-dependent EMF. This quantity right here is called the inductance. Okay, so inductance and unfortunately it has units, or it has a symbol L. That does not mean length, it's the symbol for inductance. And you can write it as the rate of change of the magnetic field with respect to current, or at least for all the examples that we will have, you can write this as phi b over I for linear materials, which is all we will talk about. In general, it's a derivative, but this is what it is for us. And it's a new quantity. It has units. The units of L, inductance, are henries. And 1 henry is 1 volt second per amp. So it's kind of a bizarre quantity, but it's a flux per unit current. That's what it is. All right. While we're on the topic, we can also talk about a mutual inductance. It's very similar. And the idea of a mutual inductance would be that if you had a solenoid like this, and you could imagine you had 2 coils. I'll draw them as separate. And you could imagine that you have a time-dependent current over here. So that's going to give rise to a magnetic field, which is also time-dependent. So we're going to get a time-dependent magnetic field here. And you can imagine that some of those lines feed all the way around to the other coil. So we get that the time-dependent current in one solenoid induces a time-dependent flux in the other solenoid, creating a time-dependent EMF in that one. So we would say in that case, the mutual inductance would be as follows. We'd say the EMF in 2 coming from 1 would be the mutual inductance of 1 acting on 2. So the time rate of change of, oh, and there's a minus sign there. So the time rate of change of the current 1 times the mutual inductance determines the EMF it induces in loops in coil number 2. The full formula then for the EMF, say in current 1, would simply be minus the self-inductance of loop 1 times d by dt on I1, and then you would have a mutual inductance of 2 on 1 And similarly, you could write the same thing for the total EMF across 2 would be a combination of the mutual inductance of on 2 coming from 1 minus the self-inductance of 2 acting on itself. So that's how we would define self and mutual inductance. They're very similar. It's just the effect of one loop on itself or one loop on another loop. All right. In the next video, I'm going to apply these formulas to some simple solenoids, basically just a cylinder, an infinite cylinder, or a toroidal cylinder, or a toroidal solenoid. And we'll find some simple formulas for the inductance.